Right, guys. Today I wrote a funny question. They said, "What we bring and why we need complex numbers." My intention today for the whole period is to try to make you see why do we need extra numbers in addition to real numbers, and secondly, to look at the things which you must know in order to be able to learn maybe in an easier way the story about natural numbers. Sorry, about complex numbers. And please, this word complex, I find it a bit confusing sometimes. Sometimes people think that these numbers are called complex because they're complicated. No. The complex part of it, for me, I understand, think for other people also, to understand is that these numbers are sort of composite numbers. Now it's a number made of different parts, which I don't want to get into that now. But first of all, what I wanted to do, what would bring to this situation is this. Let's say we're given something like this, like remove brackets. This is an exercise you know from school. Remove brackets. Let's say we're given something like remove brackets A plus B brackets C plus D. You know how to do that, isn't it? Yeah. Now, if you know, you should know how to do that, and this will help you in handling complex numbers. You will see. I will remind you when we get there. But you must remember that this property is based on the fact that if you've got two numbers, you are multiplying like this. You're multiplying this sum by A. You can always distribute that A to multiply B and then multiply C. That's what. Okay. So then to remove brackets here, we can take this bracket as our A, which is going to mean that we're going to have A plus B multiplied by C plus A plus B multiplied by D. I know somebody will tell me that you've got a shortcut of doing that one. It's fine. Shortcut is a shortcut. Shortcut is a summary. I'm trying to expand this thing in such a way that you know exactly what's happening to get to the shortcut. Isn't it? Yeah. So this is what happens. Then next thing, we repeat exactly the same way now using C. It doesn't matter. 2 times 3 is equal to 3 times 2. So this is the same thing. Then I can say now AC plus BC plus AD plus BD. My advice to you guys, please, can you try that always when we are multiplying letters? Remember, letters in this case, they are standing for numbers. You must always try to put them in alphabetic order. That will help you easily to identify common factors. It will help you to identify like terms and simplify wherever is possible, isn't it? So in this case here, are there like terms? There are no like terms. Altogether. So there's nothing to simplify. That is the expansion. My question is, what I'm saying is, this is to know how to do this thing. It's very important for complex numbers. Altogether. Then the other thing is, let's take this one. I'm taking these exercises from your tutorial I sent you, but I want you to, I'm just picking a few special ones which I need, but the other, it doesn't mean that the other ones don't need them to look at them, need to look at them. Now this one, doing exactly the same thing, I'm going to do it exactly the slow way. This is my A, in this case here, then this is A minus B by A minus B by A plus A minus B by what? By B. Then again, doing the same thing, there you get AA, which is A squared, just meaning there are two factors A. Okay? Then minus AB, you see now you can write, don't want to write BA, you write AB. Alphabetic, then here, you come here, you write again A, B, and then you get BB, which is two factors B, then you write B squared. Now if you come here, you see that there are two words which are exactly the same. They just differ by the sign. This is the plus minus. Then just need to simplify. Then this is A squared minus B squared. And this is got a special name. This is a very important identity when you look at these two. It's a very important identity. And you are going to use it a lot in complex numbers, okay? So now this is called, if I'm not mistaken, the difference of two squares. If I've got in my class somebody who's just done matric and does not know the difference of two squares, I know I've got a serious problem. This, when I look at these two things, when you put this kind of thing, you must, like, within a fraction of a second, you must know what it means. Whether you see this, you must know that it gives to that. Whether you see that, you must know that it gives to that within a fraction of a second. Otherwise, that is a problem. So these are the things I'm saying you must bring to this situation. This is the knowledge resources you must have in order to be able later to manipulate, to work with complex numbers you're going to look at now. So far, nobody knows what's a complex number. Even if you know, I don't want to tell me anything what a complex number is. But I'm telling that we are going to do the complex numbers. We are dealing with the things we need to get to complex numbers. Then also this kind of relationship, that there's a minus sign here, there's a plus sign there. That also is very, very important. Apart from knowing that these are factors of the difference of two squares, it's very important to know that and that. Are we together, guys? Okay. Then can I ask somebody to come and do this one on the board, please? To come and do this one on the board. A minus B minus square root of B and A plus the square root of B. You will see again why this kind of thing. This is exactly the same thing, but now involving what? The radical sign. Isn't it? Can I have somebody coming to do this on the board, please? Right. I honestly don't like the way it has been done on the board, because it looks like copying what has been done without showing how you are working with the things you are given. Is that right? That's my problem. Now, if I wanted to work it the long way, this way, I would do exactly this way and say A minus square root of B in brackets multiplying A plus A minus square root of B multiplying the square root of B. That is if I want to do it the long way. Then what next? Then I would do this. Multiply here and get A squared minus A square root of B plus here A square root of B minus square root of B times square root of B. All together. Then I can now come to this and say I've got square root of x by square root of x. This is x, isn't it? Because I'm multiplying the square root by itself, isn't it? That is x. If you want to change it to index notation, you can just say x power half multiplied by x power half, which will give you x power half plus that equals to x power 1, which is usually we just write as x. Altogether. Why I'm revealing all those things that sometimes people get lost in these summaries and these shortcuts in such a way that they don't really know what's happened, but they just know that this thing, when it looks like this, I must write it like this, because somebody told you that when it looks like this, write it like this. You must, when you're doing the summary, you must have the thinking process behind that thing, isn't it? So this is a square root, multiplied by a square root, you get the base, which is a. These are like terms, they're what? They're going to what? To simplify, to give us 0, and 0 plus whatever we're going to have a squared minus b. Now, if you wanted to use the summary, like for example, if you had now noticed this pattern from there to there, if you wanted to use the summary, you could have come immediately and say a squared minus square root of b all squared. I don't know where that guy got the b squared there. No. It's not. It's possible it's not a mistake. So it's possible that's not a mistake. It's the way you are doing your things with the summaries which are not understood. Right. So always copying blindly with a passive kind of mind, which is not right. So then if this thing, everybody can see that this one will simplify to that, isn't it? So that this squared we saw on the board there, we know that it's something which is kind of a mystery. We don't know how it came about. Okay, right. Any questions in that? This is called removing brackets. This is called expanding binomials. These terms like this, we call them binomials. Binomials, why? Because they've got two terms, isn't it? So you are expanding a binomial there. And I'm saying this is important for the chapter we're going to do. And what I'm explaining here also is very, very important in the chapter we're going to do. The most interesting thing here, this is what I want you to see here. You see this square root here. You see this square root here. Here, it looks like it just disappeared altogether. When you work with complex numbers, you're going to see something similar. When you see it, can you remind me of this? That the first day we looked at something like this. This is happening in the similar fashion. Altogether. Okay. Now, let's move on to another kind of thing which we're going to want to have here, which is good to have. Let's say, also this is important, I'm just going to mention this quickly. Let's say we've got 8 square root of 6 minus 20 minus square root of 24 plus 2 square root of 54. Can you simplify that to the simplest form? Preferable up to a single radical sign. I'll give you some few minutes to think about that. Right. The strategy for those who are struggling with this, the strategy is normally you try to look at the numbers under the square root sign. This is a square. You must try to see whether the number inside there is a product of a perfect square and any other number. But then a perfect square is something like this. A squared. I don't mind what a is. If you get something like what you get here is a perfect square. So your answer get there is a perfect square. So you look at this number, you say what is 24. 24 is actually 4 times 6, isn't it? And you see there's a 6 there. Then that creates a kind of a like term, isn't it? So then you write this thing here, 8 square root of 6 minus this side you say square root of square root of 4 multiplied by 6 plus 2 square root. Then again you factorize this thing in a similar fashion. square and something else. What is this? 9 times, so you write here 9 times 6. Because of the fact that xy to the power a is equal to x to the power a, y to the power a. That a could be rational root, which talks about square root, cube root, whatever. That applies, isn't it? So then you can apply that here. Then you've got the square root of what? 9, square root of 6, square root of 4, square root of 6, which gives us what? 8 minus, here is 2, square root of 4, square root of 6, sorry, that doesn't look nice. Let's get rid of that. This will be 8 square root of 6 minus 2 square root of 6 plus 3 will come out there from 9. Then you get 6 square root of 6. As you can see now, you are able to simplify this because these are like terms, isn't it? And it's simple as 2 to 12. Does it simplify to 12? Okay, 12 square root of 6. Is that so? Okay, so that is what it's supposed to do. So that also is something which you need to know how to manipulate and get the right. Okay. So if I were you, the tutorial which I gave you, I would attempt almost each and every exercise in 1, 2, and now let's get to the type of exercise number 3. And because we haven't really looked at complex numbers and we worked complex numbers, this might not, one might wonder, why is this important there? But for now, I'm telling you that this is important, and the head of this exercise says, in each of the following, rationalize the denominator. Rationalize the denominator. What is important, when you're going to rationalize the denominator, you want to get rid of a radical sign in the denominator. Now, if you think of what we've looked at before, in an expression which has got a radical sign, how did that radical sign disappear at b with a squared and the b? How did it disappear? It was multiplied by itself, isn't it? But again, it wasn't there. It cancelled out in the middle there. Why? Because we're dealing with what? The difference of two squares, or the factors of difference of two squares, isn't it? What is that suggesting? It's suggesting that if we multiply this by 3 minus square root of 3. Let me just go back a bit for where I'm talking about. I'm talking about this part here. Look, where the radical sign, the radical sign. But you multiply these two, in the final answer we didn't have a radical sign. Which means now, this could be now a rational number. If this was a square root of 2, square root of 2, this number which you're going to have here is a rational number, isn't it? So which means actually what we're doing here with something like this is a process of converting this thing to something more or less, this is expressed in terms of, can be expressed in terms of irrational, but when you do the multiplication, we express it in terms of rational. Altogether. So now when you go to the next page there and say rationalize the denominator, which means we're calling for something like this. And please, I'm going to give a name to these things now. These things, these two factors, this factor and that factor, we'll usually call them conjugate. Those factors are conjugate factors. And so one is a conjugate of the other. If I've got one, I want to look for conjugate, I'll look for the other. Is that right? So now to rationalize the denominator here, already what I've suggested there What is this suggesting? It suggests that we must search for the conjugate. All together, guys. So if we must search for the conjugate and the multiply in the denominator, that would be legal. What do you do? The only number we can always multiply with comfortable without changing the value of the number. The number is what? 1. Then we're going to multiply this by 1, which is equal to the conjugate, 1 which is equal to the conjugate 3 minus square root of 3 over the conjugate 3 minus square root of 3. So if you take that 1 and come and multiply here, what we're going to get, this, remember 1 is A times 1 is equal to 1 times A and is equals to A. So if you multiply by this 1, it doesn't matter in which color 1 comes. That 1 is not going to change the value of the expression which is given. Am I making myself clear? Are you sure? Can you explain what I'm saying, my friend?
The conjugate, when you multiply every numerator, is not going to change.
No, I don't know whether I'm hearing you properly. We are not multiplied by the conjugate. We are multiplied by 1 expressed in terms of the conjugate. You say the,
what is the conjugate?
No.
1 is equal to the conjugate.
No. 1 here is equal to the conjugate over the conjugate. Do you see what's happening here? What I'm seeing myself and understanding, and what he's seeing himself and understanding is a different thing. He's now calling the whole thing here conjugate. No. The conjugate is this thing. 1 here, listen to me, my friend. 1 here is written in terms of the conjugate. So you need to multiply the given expression by 1, which is written in terms of the conjugate. Why can I comfortably multiply by 1? Because of this reason there. Are we together? So now we go out here, you want to explain this thing to your friend, you must say it this way. You are multiplying by 1, which is written in terms of conjugate. You are not multiplying by the conjugate. Okay, so now we come here and multiply 3 minus square root of 3 now when we come here, we have a plus b, a minus b. Now if we put a plus b, a minus b, if you have learned this thing thoroughly and you know exactly what's happening, you can maybe now use the summary which says a squared minus b squared. But those things in between here must be known clearly. All together? Yeah. Then that is the case. Then you come in and say 1 times that, again 1 multiplies that, it will be the same thing. Then you come here and say 3 minus the conjugate, the put of 3, then it put on me 3 squared minus square root of 3 squared. The square root of 3 squared, isn't it? Okay. Then 3 minus square root of 3 over 9 minus 3. What will come out there is a rational number. Now we've got this thing as, we can even write it as half minus minus square root of 3 over 6. If you look what we've done there, we've written that number actually in 2 parts. One part which is what? Real. This is a real number, is it? And this one part which is what? Sorry, I was want to say one part which is rational and one part which is what? Irrational. Why irrational? Because of this. But the denominator is rational. The order of the exercise was saying rationalize the denominator. No, the denominator must be rational. Am I making myself clear? Are you sure, guys? Okay. These little things, you might look at them and say, What is this? These little things are going to be the ones which make a big difference. So please take care of them. Advice taken. Advice taken, yes or no? Can I hear the answer? Okay. Ignore it. I don't know what's going to happen to you. I don't know what's going to happen to you. Alright, so what I'm trying to do now, I'm inviting you to now look at all the exercises in number 3, which involve this kind of a thing. If you look at number 3, I actually started with an irrational denominator, which is easier. It's not a sum, it's just 1, like 3 square root of 10. And asked to find what rational denominator. There, you don't actually need the conjugate. You understand what I'm saying? But you're still going to multiply by 1. Which one? 1 which is now written in terms of square root of 10 over square root of 10. Are these two things equal? Sorry? These two things. Are they equal? Are they equal, my friend? Yeah. Okay. I hope we see that. So what I'm trying to show you, one, you can write it in infinite ways. It depends what is convenient to you at that moment you write it. Isn't it? Are we together? Okay. So I think I'll stop there and then give you number 4 as your homework. And number 4 again, I want you to express that as a single fraction without a radical sign in the denominator. But there, to say that I just gave you and said square root of t minus v over the square root of t plus v plus the square root of t plus v over the square root of t minus v, show that is equal to 2t square root of t squared minus v squared over t squared minus v squared. So I want you to work out the whole process of taking that to an expression as a single fraction with one radical sign which is not in the denominator. Same principles are going to apply. Any questions? Is it clear what you're supposed to do there? Am I talking to myself? Guys, you are looking at the exercise. I'm asking, is it clear what you're supposed to do? Okay. Alright. Let's get to this, maybe to the third part of this presentation. Let's get a new page there. Now, I think now I'm going to answer the question. I'm going to attempt to answer the question. Why do we need new numbers? Now, why do we need these new numbers called complex numbers when we've already got real numbers? We've got a lot of them actually. What numbers do we have? Remember, we've got natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. We've got whole numbers 0, 1, 2, 3, 4, 5, 7, 8, 9, 9. Then we've got integers. Integers, I hope you know these symbols, isn't it? Integers, what do we have there? 0, 1, minus 1, 2, minus 2, 3, minus 3. We've got those things there. And then we've got rational numbers. Rational numbers. This symbol here is a symbol which we use when we talk about sets, but I don't really worry myself whether you know what sets are or not. I can explain them easily. What does it mean? It means that all of these numbers are whole numbers. And all of these whole numbers are integers. And all of these integers are rational. And remember, when you get to this point here, we've got a serious problem. With rational numbers, we cannot cover all the points on what? On the line. For example, we don't have, if we've got a 1, 1 here, and this is square root of 2. We don't have this here. So to locate this number, square root of 2, we need actually to draw geometric, to locate it geometrical, which is one of the ways. Draw a right angle triangle with 1, 1 in square root of 2 there. Then put one of the points at the origin, rotate it, we will see where the square root of 2 is. And this number is never equal to something like P over Q. Remember, this is what we call rational number, isn't it? What will be that? This P will be an integer, and the Q also will be an integer. But Q must not be different from, must not be equal to 0, because the first commandment says, thou shalt not divide by 0. So then, when you've got this is a rational number, which is expressed as a ratio, 1 over 2, 3 over 2. Now, this is irrational. This is rational. Now, this is not equal to something like this. Then we say, this is irrational. Altogether, this is irrational. And unfortunately, we don't have a symbol like this for a symbol like this for irrational numbers. But I'm going to use one here for my own. I learned this thing from one guy who also doing mathematics, so I think it's fine. Because these symbols, somebody chooses them at one time, and then you get that. Then you can call these irrational numbers, and this one rational numbers. This family of numbers and that family of numbers, they have nothing in common. There is no single number which is in there and in there. So now once you have put these numbers like this, like pi, like e, like square root of 5, once you put them on the real line and number line, then you've got these two, this one and that one. Then if we take now once we collect these two, this one irrational and irrational, and bring them together in one family, we've got what is called real numbers. And that we do it this way. Say, and this sign again is a set sign, which means that you are joining the two families to make one. Altogether, then you've got real numbers. So then here, this is actually all in what? In real numbers. So the question what I'm asking there, with all these numbers, do you still need extra numbers? That's the question. But the answer is yes. I'm going to show you why I'm saying yes, and maybe you also somewhere in your adventures you have also experienced that maybe we need some new numbers. But let me just explain here something here. Let me just explain something here. I want to explain why do I say this thing is there. Remember when you count, we were talking about natural numbers. We are talking about 1, 2, 3, and so on. And this does not stop here. Altogether. But when you talk about whole numbers, you use the same symbol and it show here with a 0 that you have added a new number which is 0. Then you start counting 0, 1, 2, 3. I think everybody can see that all what is here is in there, isn't it? This is what I'm saying. This symbol can take it as saying that all what is in here is in there. Then with integers we've got a 0, a 1, a minus 1, a 2, a minus 2, a 3, a minus 3, then it goes on, and then these are integers. Now if we look, this part here is already there, isn't it? So the previous one is in this one, so this thing is true, isn't it? I think the more interesting one I was saying the more interesting one is this one when we get to rationals. Now we're saying rational numbers are entities like this, mathematical entities like this. As long as Q is not equal to 0, because if it's equal to 0 then it's not defined, isn't it? But then somebody says now, why do we say these are rational? These numbers are rational because all of them, they've got a common denominator. What is that denominator? 1. So we take minus 3 as an integer. If we want to look at it with a lens which tells us that is a rational number, we just say minus 3 over 1. And any other number, we take 41 as an integer. We want to look at it with a rational number bias. We just look at this thing as 41 over 1. I don't know whether you saw at school where you use this thing. You know, when you put a line, mx plus c, you want to plot this line using the gradient and the point. This is what you do. What do? You got a line y equals to 2x plus 1. You want to plot this line using a point and the gradient. Already you've got a point on this line. The point on this line you've got is 0, 1, where it casts the y-axis. Then you want to plot that line using only that point and the gradient. You just draw your system of axes. That is my system of axes roughly. I pick on that point 0, 1. There is 1. Then I take 2. Then I take 2 and say 2 is 2 over 1. Remember the gradient is y2 minus y1 over x2 minus x1. Then which means I must run horizontally this distance and rise that distance. So I'll come here and say run 1 and come and run 1 here and stop over 1, straight over 1. Then rise 2 and go 2 points there. Then that point is also on line. Then I take my ruler, I insert the line roughly like that. All together. That's a rough sketch. Please accept it. I know it's not very, very neat, but I'm just giving you a rough idea of what I'm doing. That's the thing. That is important now to say. That is what is where this thing becomes useful. That you must see a rational number, a whole number as a integer this way. Then, if you are given a fraction here as a gradient, you change it to a common fraction, numerator, denominator. Then you can do something like this. All together. Okay. So then, rational integers are rationals. Then obviously rationals together with irrationals, they make up reals. So the reals, the rationals and irrationals are reals, because that's the bigger family of God, isn't it? So do we still need some more numbers? That's the question. Right, we said question, do we still need extra numbers? I said the answer is big yes. Maybe somebody will say now, why do you say so? Let's look at this. Let's quickly look at this. Simple things, man. Simple things we know at school. X squared minus 3 equal to 0. Can you solve that? Huh? Somebody will say exactly x squared equals to 3, therefore x is equal to plus square root of 3. Good. Then we go 2x squared minus 8 equals to 0. What am I going to say? Say 2x squared, adding on both sides 8. 2x squared is equals to 8. Dividing on both sides by 2, say x squared equals to 4. Then you say therefore x equals to plus or minus 2. Things are flowing nicely, isn't it? Yes or no? Okay, things are flowing nicely. Then come to this one. 2x squared plus 2 equals to 0. I think someone says 8 on both sides minus 2, you get 2x squared equals to minus 2. Then x squared equals to minus 1. Then x equals to plus or minus unknown entity. Because we don't know anything like this. Put it in your calculator, you get error. That error, the calculator is telling you that you are giving me nonsense. All together. So then, unknown entity. But somebody says, really? Are we going to sit with these things with the unknown entities every time? The answer is no. We can find the solution. This is the problem. This is the problem. Then comes the problem whether you understand what mathematics is or what is the purpose of mathematics. For me, sometimes mathematics, in most cases, mathematics starts from describing a certain reality which is found in the lives of human beings or in science, whatever. So really, what you can do is, if we can, we can maybe construct a solution to this problem, or invent it, or find it somewhere altogether. Then what I can say, I will emphasize this one. This is one of the reasons why we need complex numbers. I told you, I said, go to your department, wherever, electrical engineering, go and try to find another reason why do you need complex numbers in electrical engineering, because you're engineer. In mathematics, in pure mathematics, nothing to do with buildings, electricity, whatever. For me, it's enough to find a way, to search for whether there's a way to find a solution and come up with new numbers who can be a solution to this type of equation. If you look at that, you go on with that kind of those exercises there. Most of the exercises I gave you there, the last one, you will see when you solve them, they give you entities like this, which are not defined. Somewhere you get I think one of the equations there, you get something like x is equals to 1 plus or minus the square root of minus 10. Obviously, 1 is defined, but this entity is not defined. What is this thing here? So, I think I will stop there and say, guys, this is the thing in mathematics which motivates us to look or investigate or construct or invent the thing called the entities called the complex numbers. Are there any questions? I think we've seen this thing at school, and the teachers have said unreal roots. Unreal roots. Altogether. So in this case, the chapter which we are starting on is actually going to give us a new name to this thing called unreal roots, and we're going to call them complex numbers. The only thing which is left now is that how we make sense of those entities, and then we learn what can we do with those entities and what problems in science or engineering can we solve with those entities. Then we live happy ever after with a world full of real numbers and the complex numbers. And at the end of a good discussion, real numbers also will be complex numbers. Thank you for listening. I'm going to stop there. As usual, you know me. My name is Chap. Suwazifan. Okay. Let's